The universe, as we know it, is vast, mysterious, and awe-inspiring. But what if our universe is just one of many? What if the stars, galaxies, and planets we see are only a fraction of what exists in the cosmos? The multiverse theory suggests that beyond the boundaries of our observable universe lies an infinite collection of universes, each with its own unique properties, laws of physics, and possibilities. Could this theory explain the mysteries of our existence? Why is our universe so perfectly fine-tuned for life? Are there other versions of ourselves living out different lives in parallel realities? And most importantly, what evidence supports such an extraordinary idea? The multiverse theory is one of the most captivating and ambitious ideas in modern science. At its core, it proposes that what we call the universe is merely one part of a far greater existence, an infinite collection of universes, each with its own set of properties, dimensions, and possibilities. The observable universe, with its 93 billion light-years of stars, galaxies, and cosmic wonders, might just be a single bubble in a much larger, unseen multiverse. To understand this idea, it helps to first define the universe itself. Traditionally, the universe encompasses everything that exists: space, time, matter, and energy. However, as scientists have probed deeper into the laws of physics, they've discovered phenomena that hint at the existence of other universes beyond our own. The multiverse theory finds its origins in three major areas of physics: quantum mechanics, cosmology, and string theory. Quantum mechanics, which governs the behavior of particles at the smallest scales, reveals that particles don't exist in a single state, but in a superposition of all possible states until observed. This principle laid the groundwork for the many worlds interpretation, which suggests that every quantum decision creates a new branch of reality. Cosmology contributes to the multiverse discussion through the theory of cosmic inflation. Shortly after the Big Bang, the universe underwent a rapid period of expansion. Physicists realized that if inflation occurred once, it could happen repeatedly in other regions of space, creating isolated bubble universes. These bubbles would be completely disconnected from each other, each forming its own independent cosmos. Lastly, string theory provides another perspective. According to string theory, the fundamental building blocks of the universe are tiny, vibrating strings of energy that exist in a higher dimensional space. This model suggests that our universe exists on a three-dimensional brane within a larger, multi-dimensional framework. Other branes could host their own universes with different physical laws and structures. The multiverse theory isn't just a single idea, but rather a collection of models, each offering a unique perspective on how multiple universes might exist and interact. These models challenge our understanding of reality and invite us to explore possibilities far beyond what we can currently observe. The idea of multiple universes isn't new. Philosophers and thinkers have speculated about the existence of other worlds for centuries. In ancient Greece, the philosopher Democritus suggested that infinite worlds could exist, each with its own unique characteristics. These ideas were more philosophical than scientific, but they laid the foundation for the modern concept of the multiverse. The scientific foundation for the multiverse emerged in the 20th century with the development of quantum mechanics and cosmology. Quantum mechanics, which describes the behavior of particles at the smallest scales, revealed that particles can exist in multiple states simultaneously until observed. This principle, known as superposition, inspired the many worlds interpretation, which suggests that every possible outcome of a quantum event creates a new universe. At the same time, advancements in cosmology introduce the idea of cosmic inflation. This theory proposes that shortly after the Big Bang, the universe expanded at an extraordinary rate. Physicists realized that if inflation happened once, it could happen repeatedly in different regions of space, creating isolated bubble universes. Later, string theory added another dimension to the discussion. String theory, which seeks to unify general relativity and quantum mechanics, suggests that our universe exists on a three-dimensional brane within a higher dimensional space. Other branes could host entirely separate universes, some of which might even interact with ours under specific conditions. The multiverse theory isn't confined to a single idea. It encompasses several distinct models that offer varied interpretations of what a multiverse might look like. These models stem from different branches of physics, including cosmology, quantum mechanics, and string theory, and each provides a unique perspective on how multiple universes could coexist and interact. One prominent interpretation is the bubble multiverse, which arises from the theory of eternal inflation. According to this model, the universe underwent a brief period of rapid expansion, or inflation, immediately after the Big Bang. While inflation ended in our observable universe, the theory suggests that it continues in other regions of space-time. These inflating regions form bubbles, and each bubble becomes its own independent universe. These universes are completely isolated from one another, with the space between them expanding faster than the speed of light, making direct interaction impossible. What makes this idea especially intriguing is that the physical constants within each bubble may differ. Gravity might be stronger in one universe, causing stars to collapse rapidly, while in another, gravity might be weaker, preventing galaxies from forming at all. The bubble multiverse portrays a cosmos that is both infinite in scope and endlessly diverse. Another interpretation of the multiverse comes from the realm of quantum mechanics and is known as the quantum multiverse. This model is based on the many worlds interpretation of quantum mechanics, which suggests that every quantum event creates a new branch of reality. To illustrate, imagine flipping a coin. In one universe, it lands heads, and in another, it lands tails. Now consider that every interaction at the quantum level, down to the behavior of particles, results in a similar branching process. This means that the universe is constantly splitting into an infinite number of alternate realities. Some of these realities might look nearly identical to ours, with minor variations, while others could be drastically different. For example, there could be a universe where human history unfolded with entirely different outcomes, or one where life as we know it never emerged. The quantum multiverse offers a fascinating perspective, where every possible outcome of every event has its own universe in which it occurs. The brane multiverse, derived from string theory, introduces another possibility. String theory posits that the fundamental building blocks of the universe are not point-like particles, but tiny vibrating strings of energy. These strings exist in a higher dimensional space, and our universe is thought to reside on a three-dimensional brane within this larger framework. Other branes, or universes, could exist parallel to ours, floating in this higher dimensional space. These branes might occasionally interact, producing observable phenomena such as gravitational waves or bursts of energy. In this model, the laws of physics could vary between branes, leading to universes with entirely different properties. One brane might host a universe with extra spatial dimensions, while another might have a completely alien geometry. The idea of brains adds a compelling layer to the multiverse discussion, as it suggests that universes might not be entirely separate, but could influence one another under certain conditions. The mathematical multiverse takes an even more abstract approach. Proposed by physicist Max Tegmark, this model suggests that all possible mathematical structures exist as physical realities. In other words, if a universe can be described mathematically, it exists somewhere in the multiverse. This idea is rooted in the concept that mathematics is not merely a human invention, but a fundamental framework of reality. According to this perspective, every logically consistent mathematical structure corresponds to a physical universe. These universes could be unimaginably diverse, governed by entirely different mathematical rules, geometries, and physical laws. While the mathematical multiverse is highly speculative, it highlights the potential for infinite complexity within the multiverse framework. Each of these models offers a unique lens through which to view the multiverse, reflecting the diversity and creativity of scientific thought. Together, they paint a picture of a cosmos that is far more vast and varied than we can currently comprehend. Whether it's through bubble-like regions of space, quantum branching, parallel brains, or abstract mathematical realities, the multiverse theory challenges us to expand our understanding of existence itself. While the concept of other universes is thrilling, it's important to acknowledge the immense challenges associated with studying or interacting with them. These challenges arise from both theoretical and practical limitations, making the exploration of the multiverse one of the most difficult frontiers in science. First, there's the issue of isolation. In the bubble multiverse model, each universe is completely disconnected from the others. The space between these universes is expanding faster than the speed of light, meaning no signal, information, or matter can travel between them. This makes direct observation or interaction with other universes effectively impossible using current technology. Even within the quantum multiverse, the branches of reality created by quantum decisions are entirely separate. These branches coexist, but do not intersect, meaning we cannot access or communicate with alternate versions of ourselves or our universe. Another challenge is the lack of a clear method for detecting other universes. While some theories suggest that interactions between universes might leave subtle imprints, such as anomalies in the cosmic microwave background or unusual gravitational waves, these signals are difficult to distinguish from natural phenomena within our own universe. Developing instruments capable of detecting such faint and ambiguous signals would require technological breakthroughs far beyond our current capabilities. Finally, there are philosophical challenges to consider. If every possible universe exists, does that mean the study of physics becomes meaningless? If anything can happen somewhere in the multiverse, how can we make meaningful predictions about our own universe? These questions highlight the complexity of multiverse research and the need for new frameworks to address its implications. The multiverse theory raises profound philosophical questions about existence and reality. If infinite universes exist, are we truly unique? Are there countless versions of ourselves living out different lives in parallel worlds? This idea forces us to rethink our sense of individuality and the significance of our existence. The multiverse also challenges our understanding of reality. If infinite realities exist, what makes our universe real? Does the existence of other universes diminish the importance of ours, or does it elevate the grandeur of existence? For some, the multiverse offers comfort, suggesting that every possible version of life exists somewhere. For others, it's a humbling reminder of how small we are in the grand scheme of things. Despite the immense challenges, the multiverse theory remains an active area of research, with scientists across multiple disciplines working to uncover evidence and refine our understanding of this bold idea. One promising avenue of research lies in studying the cosmic microwave background, CMB. The CMB, the faint afterglow of the Big Bang, provides a snapshot of the early universe. Some scientists believe that interactions between our universe and neighboring universes could leave detectable imprints in the CMB, such as unusual patterns or temperature fluctuations. While no definitive evidence has been found, advances in observational astronomy may improve our ability to detect these subtle clues. Gravitational wave detection also holds potential. Instruments like LIGO and Virgo, which detect ripples in space-time caused by massive cosmic events, could one day reveal signals from collisions or interactions between universes. These interactions, if they occur, might produce unique gravitational wave signatures that could be identified with more sensitive detectors in the future. Additionally, advancements in quantum mechanics and string theory may provide indirect evidence for the multiverse. By studying the behavior of particles at the smallest scales or exploring the properties of higher dimensional space, scientists may uncover phenomena that align with multiverse models. Theoretical physics continues to push the boundaries of what we know, and as our tools and methods improve, the dream of confirming or refuting the multiverse may come closer to reality, while direct observation might remain out of reach. The pursuit of understanding the multiverse is a testament to humanity's insatiable curiosity and drive to explore the unknown. If the multiverse were proven to exist, it would fundamentally change our understanding of the universe and our place within it. For one, it would challenge the idea of a single, unified reality. Instead, reality would become a vast, complex mosaic of infinite possibilities, each just as real as our own. The discovery of the multiverse would also reshape our understanding of physics. Many of the laws and constants we take for granted might be specific to our universe, rather than universal truths. This would open up new questions about why our universe is the way it is and how it fits into the broader multiverse. On a philosophical level, the multiverse would challenge our notions of individuality and significance. If infinite versions of ourselves exist, what does that mean for our sense of self? Are our choices and experiences unique, or are they just one of countless variations playing out across the multiverse? Finally, the multiverse would raise profound questions about the nature of existence itself. Why does the multiverse exist? Is there an underlying purpose or mechanism driving its creation? These questions, while difficult to answer, would inspire new avenues of thought and exploration, pushing humanity's understanding of reality to its limits. The multiverse theory represents one of the most profound ideas in modern science. It challenges our understanding of existence, reality, and our place in the cosmos. Whether or not it turns out to be true, exploring the multiverse pushes the boundaries of human knowledge and imagination. What do you think? Is the multiverse a glimpse into the ultimate nature of reality, or is it just a fascinating but untestable idea? Join us next time as we explore more mysteries of the universe.